Swayam Prabha. Digital India. Educated India.
Let's start today's session. My name is Ashruth Tambasta. I'm a principal architect at NVIDIA, and my domain of expertise is in networking. And we'll get into the fundamentals of networking as well as how we build large clusters in today's HPC data centers. So when you look at networks, what does first come to our mind? Why do you need or in a large high performance computing cluster, what is a cluster and why is there a cluster? So let's go back a little bit and see why networking came into being. Okay? So main thing was that when you a processor was created, right? Now you wanted more and more power. People wanted more and more compute, and therefore the only way of increasing more and more compute was to make the processor faster, or was to actually have more and more such processors. Okay? When you have more and more processors, you actually need to interlink all of these. You need to interlink multiple compute elements, and then you can share your load across multiple compute elements. So many things came into being. You must have heard the term SMP, symmetric multiprocessing systems. Then clusters came into being. You look at things like cache coherency. You look at concepts of message passing between various compute elements. And when all these elements come into picture, you look at bandwidth and latencies. So today we're going to cover all these fundamental concepts and kind of build up on what you already know as standard networks to how you end up making a high performance cluster using a high performance network, or what is the difference between the standard networks that you see in an office environment or in your home with traditional gigabit LAN and Ethernet, or the Wi-Fi routers, or even a large telco network versus what you do in a large HPC and AI kind of cluster. So let's go forward. So traditionally, I mean, this is a very popular picture, right? Everybody kind of recognizes this. This was one of the first Cray machines, which actually enabled connecting 4 CPUs together, and all the 4 CPUs shared a certain central memory, and they were also connected to each other for running a parallel workload. Okay? And to connect all these elements together, there was some inter-CPU communication and control. This is where networks for HPC comes into picture, right? You need to have some sort of mechanism to distribute the workload between various CPUs. You need to have this mechanism to coordinate between the various compute elements. You need to have this mechanism to do some sort of memory locking, so that if one element is writing on a certain section of the memory, then the second compute should not be overwriting that, and so on and so forth, right? So now this is traditionally how it started, but humankind has always been not satiated with simple stuff, so we wanted more and more. So I said, okay, now why don't we keep on adding more and more CPUs? And now you can see that over a period of time, or if you keep adding more and more CPUs, you cannot, the complexity that is required to connect them together starts increasing manifolds. The central block that you see on this picture, the inter CPU control and communication part, it becomes more and more complex, and there is only a certain limit to which it can handle the number of compute elements. And this is where industry started moving into something called clusters. And starting from that, standard typical SMP machines to these large modern supercomputing clusters is a journey of various technologies. We are going to be covering the networking portion of this. So in a modern supercomputing cluster, you do have hundreds and thousands and even tens of thousands of these compute elements. But now they cannot all connect into a central location, because imagine, what is the central location? It is, after all, some sort of logic. It's a it's a silicon device, right, which will coordinate between all this. Now imagine if you have to connect 1,000 processors to a single silicon, trying to coordinate and do data passing between the compute elements. It's impossible to construct. And that is where standard high performance networks comes into picture, where now we are able to link tons and tons of CPUs together to create a single large supercomputer. The programming paradigms, the use cases have changed quite a lot, because if you look at a standard symmetric multiprocessor machine where a whole set of RAM was completely shared and exposed to all the compute elements, you cannot have it in a clustered environment. So a new paradigm of exchanging data came into play, which is called message passing, with which most of the people who are into HPC domain or AI domain are aware of, right? You need to have some sort of a communication library that packetizes the data from one CPU element and then sends it across to another element, and it does it using some sort of messages, which is what we call as an MPI, message passing interface, right? So uh, to do all that, you need to have the basis of connecting all these elements. When you say message passing, it's a very higher layer of abstraction. It is in the domain of coders. But before that, we need to create a cluster, and that is what we will talk about from the fundamentals. What are the design principles? What are the limitations? And what limits us in going from A to B? Okay, if let's say today I'm saying that we are able to construct a cluster of 20,000 elements, why can't I construct more than that? If I'm saying that today I have a certain amount of bandwidth between the elements, why can't I increase? Or why can't, what is the limiting factor? What technology defines the limits? So we will look at those limits, and hopefully people who are interested in this domain will be very interested to continue research and see it as a challenge. Okay, why is this limit there? What is the state of the art today, and how it can be improved? Okay. So with that introduction, let's get on to today's session. um, so when you look at the networking components for a high performance cluster, you actually break it down into 3 4 elements. Okay, you have, why do you need this networking? You need this networking because you have a large enough job which cannot fit into a single compute element. You need to distribute it amongst multiple compute elements, and therefore you have multiple compute elements that you see on the left. You have some sort of interconnect media that you will use to connect this to another element. But now, since your cluster is not only a point-to-point connection between two elements, you need to have uh, hundreds or maybe thousands of compute element. You need to have that central interconnect unit, which is where we bring in a switch, a network switch, or a combination of multiple network switches. And therefore you have a end interface device, which is called a network interface card or a host channel adapter in various terminologies. It is nothing but an interface which kind of talks to the processing element, is able to address the memory of the processing element, and it's able to send data from its port externally to a particular switch, which will receive the data, try to make sense out of it, and then send it across to its destination. Okay, so there is a element inside your compute, which is the channel adapter or a network adapter. There is an interconnect media, which are nothing but your cables. There are switches, and why, and the same thing repeated again, right, for the destination side. So we will look at all of these elements, and we'll mostly look at the fundamentals of the fabric, which is from the compute to another compute, what are the elements involved. So before I go there, let's do a little bit of history. So if you look at the HPC interconnect history and development, it starts right down from, I think, the early 90s, where we had Cray as one of the leading supercomputing companies. They started off with a crossbar interconnect to link multiple of the compute elements. Okay, then there was an explosion of multiple standards and technologies by the end of 1990s. Okay, so towards 1999 and 2000, there were companies like Quadrix, Myricom, and Mellanox, which standardized high performance interconnect for HPC and HPC cluster. Actually, there was no AI back then. Now AI comes into picture, and we will talk about how the fundamental requirements of AI are completely equivalent to what HPC systems need. Okay? So the systems that we design for HPC now are actually being called HPC/AI systems. So yes, many companies started off, and there were a lot of standards. Okay? The whole aim of all these standards was to have the fattest possible pipe between the compute elements so that we can transfer the highest amount of data fast in the least amount of time, which corresponds to your bandwidth. It also aimed at reducing the latency of these transfers, because every time when you were doing parallel compute loads, people would not do very large data set transfers. There might be simple communication wanting to, like a mutex kind of communication, right? Or simple flags, or simple single element data exchange. So it was imperative to have these network be very low latency, because whatever time that is spent by the data in flight is the time no compute can happen, right? If you're looking at synchronous compute and communication, uh, the time spent on moving data from one point to the other is time wasted. So you had to have very small, as small as the latency as possible. So the two fundamentals for high performance networks for building clusters was high bandwidth and low latency. And over the years, many companies, did a lot of things. And right now, if you look at today's scenario, two of the companies are surviving. One is Mellanox, which was actually purchased by NVIDIA, and it is now, which was the proponent of InfiniBand as an interconnect technology. The other is Cray, which got actually acquired by Hewlett Packard, HPE, and they propagate their own proprietary interconnect for making supercomputers. Some other companies came into being, but then they have stopped manufacturing HPC networks. Again, this is more of history and technology and companies where things stand today. But what we will discuss is the fundamentals, okay? And then we'll map it into the current generation. So let's go into the fundamentals. I thought of having this session with top-down approach, where we will talk about today's cluster, and then we'll drill down into the underlying technologies. But since this is more of a knowledge sharing session, so I thought let me do a bottoms up approach. So we start with the fundamentals. The fundamental is the physical layer. Okay, if you have to connect two elements together, you need to have some method of connecting it. And what are we aware of? Okay, so first of all, when you look at the physical layer, it is nothing but a wire. It can be a wire, right? You take two elements and you connect a communication cable between them. And what does this cable do? Well, actually, it just transmits zeros and ones, right? It sends out sequences of zeros and one. And there are various, people who are from communication engineering background, they know that there are various methods of sending these zeros and one. You can have different kind of coding, you can have higher frequency, and so on. And that's what we do today. Okay, and the thing that we are most commonly aware of is a standard LAN cable, right? A LAN cable, RJ45 cable, contains copper conductors inside, and there is a certain speed at which you send the bits, you send the zeros and ones. in today's world, we are looking at sending the zeros and one over a single pair of copper conductor as fast as at 25 gigabits per second, or even 50 gigabits per second. Okay? And depending on what kind of signaling are you doing, if you're doing non-return to zero, where zero corresponds to 0 volts and one corresponds to a high voltage, or you can divide the levels of analog signal by in multiple levels, represent every level to a particular bit pattern. So you do amplitude modulation, right? So you do different kind of signaling, but it is the media that transmits the data between these two compute elements. Now, the, one nice thing we've seen, over the years, uh, there are so many ways of doing this thing. Okay, and every time what happens is, one company propagates a particular standard, another company propagates another standard. Okay, one says, okay, my analog designers are good to send bits very fast, so they can design their ICs so that the switches are very fast. Okay, so I can do 25 gigabits per second, but another company says, hey, I've got engineers which cannot design the on-off control so fast enough, but they can do it very accurately. So I can do multiple levels of analog voltages. Okay, so I will propagate a standard which is non-return to zero, and it does a modulation, different kind of modulation. So there are so many things. One company says, okay, I will send it across one pair of copper conductor. Other company says I will send it across 4 pairs because I can do parallel. Okay? So all this resulted in multiple competing standards, and then there's always a consortium of companies. They come together and say, hey, it's ridiculous, we need to develop one universal standard that will cover everything, and it will cover everybody's use case. And eventually what happens, it results in another standard, a 15th standard, right? So now there are 15 competing standards. Again, there is no I would say there's no way of uh, addressing this. This is how it has been, and therefore we try to achieve as much standardization as possible. But because HPC and AI, or high performance networking for HPC and AI cluster, is such a niche, I would say, field, that whoever does things the best and the fastest gets a standard, okay, or puts things in a standard. So let us look at, when we talk about standards, let us look at some simple things. I'm talking about connecting servers together, right? When I'm talking about connecting servers together, I'm looking at these physical media connectors. Okay? You all are aware of these standard LAN cables. It contains multiple copper conductors inside, and it connects to your simple RJ45 port, and it basically sends out data. But this, as you all know, is not very suitable for very high speed networking. What's the maximum that you see? You see a maximum of 1 gigabit per second, or you see a maximum of nowadays 10 gigabit per second, right? In HPC or AI clusters, we are looking at 400 gigabits per second. Obviously, these standard links are not capable of carrying that much, and we will touch a bit of why they are not capable of carrying that much. Okay? Therefore, you have standards which are based on SFPs, standards which are based on QSFPs. These are various connectors which are used to link two systems together, or link a system to your switches. Okay? And they have different capabilities. But the fundamental capability comes from the fact that you need to send data as fast as possible. What are the knobs that you can tweak to send this data fast enough? What you can do, we talked about simply encoding, right? So you can encode more rather than having a voltage level represent a 0 and a 1. You can actually do encoding so that you can carry 2 bits in every clock cycle. You can increase the clock cycle itself. Rather than clocking data at 25 gigabits per second, you can do it at 50 gigabits or 100 gigabits. You can use multiple physical channels. so that when you connect two systems together, if you go in your normal RJ45, there are four twisted pairs, right? Why is it called UTP, twisted pair? So unshielded twisted pair. There are four pairs of copper, so you can have more parallel lanes to increase the bandwidth. Okay? Or when you're going optics, you can start multiplexing multiple wavelengths into an optical fiber. So all of these parameters have got certain limit, and limits are very much related to current technology, physics. So I will just concentrate 5 minutes on one of the limits, or how this limit is reached, right? Let's look at a standard high-speed channel between a transmitting element and a receiving element. That means between server 1 and server 2. Whatever is there inside the server, it's a black box. So this triangle, it is the transmitter. It represents that black box. It goes into a connector. The connector goes into a channel. The channel can be a cable. It can be a backplane of a large supercomputer where you plug in multiple servers as blades. Okay? That channel carries signals. There is a receiver connector, and then there is a receiver amplifier. And therefore, this entire thing forms a high-speed channel. What now, when we are sending data on this high speed channel, you send it in zeros and ones. You must have seen in many interconnect related blog posts or papers that you study, you always see something called an eye diagram. Whenever there is a high speed network shown, it shows a very nice diagram which looks like an eye. This one is not looking like an eye, but I just want to show you why I have it here. What is an eye? What is this diagram? It's nothing but a representation of the bits that are being sent from one server to the other. The bits are these zeros and one. Every 0 and 1 has got a bit period. The period of this bit is nothing but the reciprocal of the frequency. So if you're doing transmitting data at 25 gigahertz, the bit period is certain amount of nanoseconds. So if you plot all the bits in that window and then overlap all the other bits, you will see something that looks like an eye, okay? Where x-axis represents the period of your bit, y-axis represents the amplitude of your bit. If now let me go here, this looks more like it, right? This looks like an eye. This is nothing but the bits that are actually traveling through your interconnect channel. And this is what people who are electrical engineers who are working on circuits with high-speed networking would see. This diagram just represents that if there is a zero, or if there is a which is mapped to the negative voltage, if there is a one, it is mapped to the positive voltage, and the margin in between where I have no bit present or no sample present is my margin. That means my receiver can distinguish between a 0 and a 1. Why it can distinguish between a 0 and 1? Because the voltage levels are distinct over here. So if I have a comparator, I can make out what is a 0 and what is a 1 by comparing against a level crossing. Okay. When we are transmitting this data through a channel, the bit period or the eye diagram starts looking somewhat like this. The eye, this is what we say, that the eye is closing. What it means is now at the receiver end, I'm not able to make out, or there are times when the channel is very long, the eye completely closes. So there is no more black portion in the center over here. Therefore, my receiver cannot make out whether it has received a 0 or a 1. So this defines one of the fundamental limits. Okay, why? Unless and until if you are able to make out between a 0 and 1, you have not actually transmitted data from the source to destination. What defines this fundamental limit? This is where we come into. So I'm getting into why, what are the limits right now, or why we cannot, why do we have only 10 Gbps? Why cannot I make 1 Tbps today? Okay? The reason is that I have a certain media, okay, and it has got certain characteristics. It has got certain kind of loss characteristics. Every media has got frequency dependent, I would say, conductance, right? So when you start increasing the frequency of the electromagnetic wave that you're transferring, the amount of resistance that it offers, it increases. There are more losses. Okay? And channels are not capable of keeping up to a certain speed limit. Why they are not able to keep up with a certain speed limit? Again, you go into the physics of it. There are copper losses, there are reflections. I will talk a little bit about that. But what happens is, why do you see that closing eye? You see that closing eye because when you are transmitting zeros and one, it can be any random pattern. It is not 0 1 0 1 0 1. It can be multiple zeros followed by multiple ones, or some zeros, some ones, or it can be even 0 1 0 1, depending on what signal is going. When you look at that bit period or that bit diagram, uh, multiple zeros followed by multiple ones, it's a lower frequency, right? Because the time period is high. When the bit pattern is a continuous sequence of zeros and ones, the frequency is higher. So you're actually transmitting a wide range of frequencies. It's a wide band. And obviously, when you transmit the lower frequencies, the attenuation of the media to these frequencies correspond to this side of the spectrum, the left side of the spectrum. When you go on higher frequencies, you have more attenuation. That is standard property of copper conductors. When you're transmitting electromagnetic waves, it's a transmission line. There is obviously a dielectric. There is a ground reference, there is a plus and a minus, and there is a dielectric in between. When the electromagnetic wave is going through the media, the dielectric also needs to polarize and depolarize at the same frequency at which you are transmitting the waves. Obviously, this dielectric's ability to polarize and depolarize causes frequency dependence of insertion loss, and because of which higher frequencies get attenuated more, lower frequencies get attenuated less, and you see a closing eye. So these are some of the limits, and therefore, industry obviously moved to optics. There are tons of optics out there now. Why? Because, well, insertion loss in optics we know is very less. Okay, when you're sending an optical wave, it goes through optical fibers and you don't get so much insertion loss. So now I can carry longer distances, I can carry more speeds. But when you go into optics, you require more power, you require more energy, you require more complicated electro-optical converters. How do you launch data into the optical fiber? Basically, it's nothing but a laser which is being turned on and off at the same frequency as your data rate, right? And the laser, when it turns on, it sends a pulse of light, and the photo detector detects it and then converts it back into electrical signal, makes it a 1. If the laser is off, it is a 0. There are other technologies that people work on now, which is related to photonics, where you also try to modulate, instead of turning the laser on and off, you try to modulate the laser so that you operate in a region where you have lesser delays between turning on and turning off, and therefore you can transmit data faster, and so on and so forth. So starting from standard LAN cables, or if people, people from the 90s would also remember standard modems, right? Cable modems, telephone modems, in which we used to get kbps of speeds, right? Because it was, a certain kind of media. Uh, Standard UTP connectors would give you that time 100 Mbps. So starting from that, today the industry is able to do with single ports link speeds of around 400 gigabits per second. So this is where we solve the bandwidth problem. And of course, there are developments going on in which we would actually increase it from 400 to maybe a terabit per second and beyond. So this is on the physical side. Definitely, we don't want to spend all our time on the physical side. So let me come into the next side.